All right, so as we saw in class, we kind of rushed through these three distributions, the binomial, the geometric, and the Poisson. So this one is going to be a geometric distribution. And we're going to try problem number 12 on page 220. And there's three parts to this problem. Now the formula for this problem is pretty simple looking, but it should be common sense. And also on page 219, if you write that down, it gives you a summary of all those distributions all in one spot, which is really nice. But the formula that we're using is P times Q to the x minus 1. And if you think about it, this distribution, and it's defined for you right on the top of page 216, so write this down so you could go back and refer to it. But it says, you might have, the problem that they say you might have to send several emails before it's successfully sent. A geometric distribution is one where you want to find out at which particular trial do you actually get a success. How many times do you have to try something before you actually succeed? And that's on the blue box on the top of page 216. So we're going to try something over and over again until we get a success. And what's the probability that we get a success on the 5th try, or the 3rd try, or the 10th try? So how many times do we have to try this before we actually succeed? In number 12 on page 220, if you want to read along with me, it says an auto parts seller finds that 1 in every 100 parts sold is defective. Let's call that our P. And even though it's saying it's defective, if they're asking about that, we'll call that our success. And 1 out of 100 is also 0.01. That would mean that, and these are defective parts, that would mean that 99 out of 100, or 0.99, are not defective, or they're the good parts. All right? So we're going to say, let's just call this, these are the bad ones, and these are the good ones. So now that we know that, part A says find the probability that the first defective part is the 10th part sold. So in other words, what's the probability that we find the first defective part as we're going through there being the 10th? So in other words, the first 9 were good. There's no 0 tries in a geometric distribution, but the first 9 we have good parts, and then all of a sudden we get a bad part. This formula would actually be better written like this. Because think about it, what I'm getting is I have a 99% chance of getting a good part the first time, times the 99% chance the second time, and I want to get a good part the 3rd time, and I want to get a good part the 4th time, and it goes on and on and on, right? And what happens is we can call this 99. I want 9 of those good parts, and I want the bad part to happen on the 10th try, which we call the bad part is the success, because that's what they're asking for. And if we multiply these together, what we get is an answer of 0.009. So it's a very, very slim chance that we're actually going to get a bad part on the 10th try if 1 out of every 100 parts is actually bad. So that's part A. Part B, they turn it up a little bit and they get a little bit more complicated. And they say, what's the probability that the first defective part is the 1st, 2nd, or 3rd? So what I do is I say, well, what's the probability that X is actually the 1st, the 2nd, or the 3rd? Or being the key word, which implies addition when we're talking about probabilities. So let's think about this. If we got a defective part on the very first try, the chances of that happening are 0.01. So getting this would be the probability of getting a defective one on the very first try, plus the probability of getting a defective one on the 2nd try. Probability of getting a bad one on the 2nd try is going to be, well, let's see what's happening. I get a good one first, and then I get a bad one. So I'm only 2 tries. The first try is being good, the second try is being the bad one. Or, which implies addition again, I'm going to have the bad one be on the third try. That would mean I would get 2 good ones, right? And then a bad one. Or we could write this as 0.99 to the second times 0.01. And if you can see how that formula applies, look at this. P is just always P. And Q is always going to be what we're interested in. So this would be plus P of 3. This 3 minus 1 is the 2. So take a good look at this. Practice this over and over again. See if you could come out with the answer 0.0297 as your final answer for that one. Now part C is kind of strange. They're saying, what's the probability that none of the first 10 are defective? The probability that none of the first 10 are defective. So we want none of these, right, for the first 10 tries. Now this doesn't necessarily imply that the bad one is going to come on the 11th try or the 12th try or whatever. It could go on and on and on. But what we're saying is that we want a good one on the first try, we want a good one on the second try, on the third try, on the fourth try, and so on. All the way up to the 10th try. So this would be 99 to the 10th. This number comes out to be 0.90438. So again, we're not multiplying by a 0.01 here at all because we're just saying what's the probability of not getting a bad one at all. Now, the other thing you can do for this one doesn't have a table in the back, the geometric. So when we get to the next one, Poisson, that does have a table. Binomial has a table that we could add to. This one is more just common sense. And I like when the formula is written backwards better because it's saying, if you want what's the probability of getting a success on a certain try, you're saying, well, how many failures do I have before I get a success? If the question was, what's the probability you get a success on, say, the 5th try? That would mean that I would have to get 4 failures and implies multiplication, and then a success on the 5th try. And I would multiply those out on my calculator. So practice these and try to do as many odd problems on page 220 and 221 as you can. And look forward to the next video, which is going to be on Poisson distribution.